Hi, I'm Randall Hayman, a mathematics academic. During the coronavirus outbreak, I'm using my YouTube channel to help anyone who wants help with mathematical problems and concepts. So if you're a lecturer, tutor, high school, primary school teacher, parent, grandparent, student, and you'd like me to make a video for you or your students, use the comment section below the video or send me an email, which is the email address is up here. So Benny Lowe from Fremont, California, has asked me to prove this, which is fine. He actually sent me a solution that someone else did on PDF. It's quite okay, but I'm choosing to do it a slightly more fulsome way, which I think will be better for people to understand it. So let's start. But before we do that, we've talked about integral domains quite a few videos, and we went through the definition of an integral domain if you need that. This here, this dx, this is just the set of polynomials with variable x, and every coefficient is an element of the integral domain. And we talked in the previous video about units. A unit is something that divides the multiplicative identity. So for example, in Zx, well, in Z, we have the numbers. There are two numbers that are interesting for what I want to say. We have -1 and 1. Both are units. Well, 1 times 1 is 1, and -1 times -1 is 1. So -1 and 1 are both divisors of 1. And what this is saying is that these -1 and 1 are just the units in the ring of, or the integral domain of polynomials. So Zx, in Zx, we have sort of fx equals -1 and fx equals 1, or both of these are divisors of the multiplicative identity or the unity in Zx, which is 1. If you like, you can think of this -1 as -1 plus 0x plus 0x squared plus. This just shows you that it is in fact a polynomial. It's a constant polynomial. Okay, so we've sort of got a bit of an idea where we're heading here. So let's see how we do with this proof. So I'm going to let A be the set of F that are elements of D, such that F is a unit. And I'm going to let B equal the set. I could put here fx or f. I might actually just put fx, which is just to reinforce that it's a polynomial, such that fx is a unit. Now you've got to be careful with this problem. This is saying, because it says just here, just the units of D, this is basically saying that if we take the elements of D that are units, consider them as polynomials in dx, well, the only units in dx are going to be the units in D, and vice versa. So the two sets are essentially the same. So here I can reflect that by just saying it will suffice to show that A equals B. This is actually quite a good little trick in mathematics. Often if you're trying to prove something, it can get a bit convoluted and you're relying on a lot of English, and often if you can express as sets and just show that the two sets are equal, well, that's a good way to progress. It will suffice. So firstly, then the next trick is, how do we show that two sets are equal? The best way generally is we show firstly that A is a subset of B, and then we're going to show that B is a subset of A. First we show A and B, and then we could write it like this. B is a subset of A. This bit says B is a subset of A. And so In fact, we're not going to say firstly anymore because we'll say that in a sec. So we'll just say we show, and thus A equals B. So what I'm saying is if we show this and this, the proof is done. Okay. So firstly, we show A is an element of B. The best way to do that is to say, suppose F is an element of A. So F is also an element of D. It's an element of the integral domain, and there exists. I don't have to put A there. There must be some G that's also an element of D, such that G or F such that F times G equals 1. That's the definition of F being a unit, that it divides 1. Okay, so now we can just recognize that F is actually equal to F plus X1, So this is a constant polynomial, but it is actually a polynomial. F1, X1 plus dot, dot, dot. Actually, we can just, I suppose we could do plus dot, 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 Fm, Xm, where Fi, all these Fi's are equal to 0. And I suppose we better make M, in this case, greater than or equal to, well, I suppose it could equal 0. Yeah, that'd be okay. So we could actually make this greater than or equal to 0. And G, and and also, I'm not letting it, it actually follows, and also G is the same as G plus G1 X1 plus Gn Xn, where the GIs are all equal to 0 for all I, and N is greater than or equal to 0. Let's just make that a bit clearer. So also that, okay. Then we see that F is an element of D and F is a unit. Since, just to repeat, if we multiply now the F and G in the way we've expressed as polynomials, we'll get 1. So A is a subset of B. Okay, so that was probably the easier bit. Let me move this up a bit. So now next, we will show that B is a subset of A, which I wrote before. I wrote around the other way, but essentially it's the same thing. B is subset of A. Okay, how are we going to do this? Okay, so suppose this is just the autopilot normal first line. Suppose Fx is an element of B. So Fx equals F naught plus F1 X1 plus Fm Xm, where Fi is an element of D. And I think I'm not going to write all the time for all i's, so that's just sort of understood. M has to be greater than or equal to 0. So, okay, since Fx is a unit. How do we know it's a unit? Because it's an element of, we wrote here fx is an element of b. If you look back to the definition of b, it means it's a unit. Since fx is a unit, there exists actually, what I'm going to do is this, actually. What I'm going to do here is, I'm going to say that fm cannot equal 0. So what I'm doing is I'm saying I'm expressing, this is a polynomial of degree n. And so it's important that fm here, fm is not equal to 0. Okay, since fx is a unit, there exists a gx that's an element of b with gx equal to g naught plus g1 x1 to the power 1 plus gn x to the n, where the gi's are, all the coefficients are elements of the integral domain, n is greater than naught, and gn is not equal to 0. Once again, this is g is of degree n. Okay, so we've got that, but there's also, so that's the g, that's the form of g, and fx times gx is equal to 1, because that's, I mentioned up here, fx is a unit. That's what it means to be a unit. Okay, so we have, so I'll write it around the other way. F1 equals fx times gx, and that'll equal f0 plus f1x to f blah, 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 plus fm xm. Actually, just doing this, I realize I don't need to. I can just go g0 plus dot 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 plus gn x to the n. Okay, and that equals f0. Actually, let's write it this way. So 1 is equal to f0 g0 plus, then there's all these other terms, and finally there's fm gn x to the m plus n. Okay. So if m plus n equals 0, then 1 equals f0 g0. And so, well, fx is equal to just f0, and gx is equal to g0, and thus these are just constants now, f0, g0. We've seen that they're units, and so thus fx and gx would be elements of A. Yeah, they're just elements of D, and they're units, so they're elements of A. So that's the case where if m plus n equals naught, if m plus n is not equal to naught, so this is proof by cases, we're going through the two cases, only two cases. So if m plus n equals naught, then if we equating powers of x to the m plus n in 1, this equation here. So on the left-hand side, we've got, what are the powers of x to the m plus n on the left-hand side? We've got 0 here, this 1 here, up here, or this 1 here. Well, the 0 is the power of x to the m plus 1 there, and so that must equal fm gn. Okay. Yeah, correct. Now, since fm, gn, and gn are elements of the integral domain, well, I'll just put in brackets, which has no zero divisors. I've done a video on this a few back. What does this mean? That it means that, which means then FM is equal to 0 or GN is equal to 0. So if we go back to this line here, we're saying there are two things that we multiply to get 0. We know in an integral domain that we can't have, you can't have here two non-zero elements. So either FM is equal to 0 or GN is equal to 0. And we can't have that because if FM is equal to 0, this contradicts our definition of fx. If you go back to fx, we said that FM cannot equal 0. Now we're saying it is equal to 0. And if Gn is equal to 0, this contradicts our definition of Gx. So what we're saying is, so we can't have m plus n is greater than 0. So let's just go back here. Or I put it up here, m plus n is not equal to 0. So let's just write that there. So if you look back what we've done here, we've said let's assume that fx is a unit. So there's a gx and fx times gx equals 1. We've laid out all the condition. We've sort of put down the polynomial for fx and gx. And up here, we do if m plus n equals, if the sum of the degrees of f and g are equal to 0, well, then we see that both f and g, and in particular fx, or f, is an element of A. It's an element of D, and it's a unit, so therefore it's an element of A. And then we showed that if m plus n does not equal 0, well, we get a contradiction. So we can't have m plus n not equaling 0. So therefore, we've shown that B is a subset of A, and we can conclude that B is equal to A. We've shown that B is a subset of A is a subset of B, and so B equals A, which concludes the proof. So we said that it would suffice to show that B equals A. We've shown B equals A, so this concludes the proof. I hope that's been useful to Benny and anyone else that's watching, and Benny's students. If you've got any questions on this, let me know, or any other questions about mathematics, put a comment below the video, or you could send me an email to coronahelpmathematics@gmail.com.